Everybody, and welcome back to another fun and exciting pre-calculus class. In today's lesson, we'll be jumping into lesson 14.4, polar graphing analysis techniques. All right, so basically, here's what we're doing. We're continuing talking about polar graphing, but in this lesson, we're going to talk about 4 different ways. And I think in this lesson, I'll probably get 3 of the 4, and then probably I'll attach the 4th to the next lesson, 14.5. As I was looking this over, that's kind of the plan. We'll see. I might be able to get all 4. If not, I'll attach it to the next lesson. All right, so let's jump into it. Go ahead and look down here at your book, and this is on page 281. So what we're going to be doing here is we're going to be in the first analysis technique. Okay, so there's 4. The first one, we're going to be converting to rectangular form. Now, we've already had a lesson on this, so I'm not really going to teach it. I'm just going to teach you kind of the why behind it. So the why behind it is, let's go ahead and look over here at the screen. I'll go ahead and teach from over here for a second, and then we'll jump back to the book. So the why behind it is that sometimes converting to rectangular form can help us simplify the graphing process. In other words, sometimes it's a whole lot easier if we do it that way. Okay. Now, to do this, what we're going to do is we're going to overlay a Cartesian plane on top of our polar graph. So it's going to look like this. So here's our polar graph, and then I'll zoom this in so you can see it just a little bit better. So everywhere that you have, like on the x-axis, you'll have 1, 2, 3, 4. So every one of these rings will be another number on your x-axis. And you could do this like we did it before, where it's 1.1, 1.2, 1.3, or 1, 1.5, 2, 2.5, 3, whatever scale looks best for the graph that you're actually putting on the graph paper. Now, this is something that's new. Here on this one, we have the y-axis also kind of marked off. So in other words, when we get it to x and y, that way we can count over 4, and we can count up 4, and we could put a point over here at 4, 4. So we're using our coordinate points to graph on, technically, yes, on the polar plane, but in this case, on the Cartesian plane as well, because we've overlaid it on top. Hopefully that makes sense to you. Again, you could put this just into the polar points, but it makes it a lot harder. So let's go over here and look at an example. So in this example over here that's in your book, they give you rho equals 3 secant theta and rho equals 2 over cosine theta plus sine theta. Now, you could graph it from right here. You have everything that you need. You have your rho, and you could figure out what your theta is. The problem is that when you do that, it can become a little bit difficult sometimes to plug into, because we don't have a secant button on our calculator, for example. And on this one, it's a little bit more challenging because we have cosine and sine. So sometimes it's just easier to graph these using rectangular. So if we convert, let's convert the first one, 3 secant theta. What we'd use here is our identity. Our identity for secant is 1 over cosine. So basically we multiply this, or we change this to 1 over cosine. And when we do that, we would get 3 times 1 over cosine theta. We multiply that out, we get 3 over cosine theta. Okay, so there's our rho. Then if you'll remember, going back to the lesson that we did on converting from polar to rectangular, we would want it to be in the form of rho cosine theta, because that's the one that basically equals our x coordinate. And so we would get x, when we sub it out, we get x equals 3. If you don't remember how to do that, we've got a whole lesson on it. So go back to that lesson and review it. All right, so we get our x coordinate is 3. And from this, we remember that if we don't have a y, then y equals 0. So our coordinate points would just be a line. So here's that line right here at x equals 3. Okay, vertical line. Now this one over here also gives us a line when we do this conversion. And again, you've got to go back to that lesson that we did on converting. but we're going to multiply each side by cosine theta sine theta. That's going to get us rho times cosine theta plus sine theta equals 2. Then we would distribute our rho to both of those, and then that equals the x and the y, or the x plus y. So once we get that, then we have that in a format that we can handle. We could convert this to y equals mx plus b pretty easily by moving the x to the other side and getting y equals negative x, and that would be 1 over 1 slope plus 2. And so there it is right there. That's that line. So sometimes these polar equations actually just give you lines, just like a rectangular equation would. So sometimes it's easier to convert that rather than to leave it in polar and graph it as polar. So you kind of have to figure it out, like, is this going to be easier to graph in polar, or is this going to be easier to graph in rectangular? And then you make your decision based on what to do from there. Go ahead and turn the page over, and we'll talk about finding branch tangents at the pole. And you say, what is a branch tangent? Well, it's a good question. We haven't talked about that yet. So in a polar graph, a branch is a portion of the curve. And as I know you've kind of learned in geometry, and we'll be talking about more in calculus at some point if you continue there, is a tangent is just a line that touches the circle in geometry, or touches the curve in calculus at one point. It only touches it at one point. So in this case, if we kind of look over here, this line right here only touches it down here. See this curve? It only touches it right here. This line right here only touches it in one place as well, right here. So these are called tangents. Branch tangents at the pole means that these lines, they originate from the pole and they go out. If you look at this line right here, this one that's kind of in the middle, this line touches it twice, right? Like it cuts through the middle of it. So this would be more like a secant, but this is definitely not a tangent. This one only touches it in this one point. It like brushes up against the curve and only touches it in one point. This is the only point from the pole that does that. So here's the pole, here's the basically 0, 0 line, and there's only one line that comes out. So anywhere else you go in this, it's going to be cutting it and not touching it at one point. So there's only one spot that goes here, and there's one spot that goes up here. Now, what are these tangent points? It's actually fairly simple. Here it is right here. Branch tangents occur when rho equals 0. That's all you need to know. Okay, so coming over here, looking at my screen, branch tangents only occur when rho equals 0. They are drawn as straight lines from the pole. Okay, that's all we do. There's nothing fancy here. We just figure out, okay, does rho equal 0? If it does, it gets a straight line at that degree, whatever degree that's at, and we move on. Jump back over here to the book, page 282, and take a look at this. So as we're kind of building out our charts, this was from last lesson where we talked about how to do this. So here's our theta, and here's our rho. Remember, our rho, there we go. And so as we do this, when our rho equals 0 at that degree, so at 0, we're going to have a branch tangent. So look down here, at 0, so 0 degrees, we're going to draw a line, a branch tangent. That's this line right here. You can see these little arrows as they go out. Now, we would keep going and say, does 0 occur anymore? Because these things a lot of times repeat themselves, right? So as we go around the circle, sometimes we have another 0. So look, there's rho 0 at 60. So we'd come over here to 60 degrees. And at 60 degrees, we go from origin and we follow 60. And look, it only touches it in one point right down here, just like 0 only touched it at one point. We'd keep going. We'd find out at 120, we have another branch tangent. So at 120, we have another one. Again, at 180. And you can see it once you get it on the graph as well. And then you see it here. It only touches it once at 240. And then here at 300, and then back here at 360. So you'd have one on the 0 and one on the 360. So don't forget that if it asks you for what are the branch tangents. You would also need to put one at 360 because the circle comes around and it closes back up at 360. So make sure you get all of those branch tangents. So in this case, we'd have one at 0, 60, 120, 180, 240, 300, and 360. So look over here at the next page. They kind of do another one. It's the same exact thing. So in other words, we take our equation and we plug it in, and we plug in 0, 30, 60. Now, here's the thing that might happen, and it just kind of depends on the equation. But if you see it kind of curving, you might need, this is where you might need to put in 15, 45, 75. You might need to put in a number of different things to get your zeros out of this. All right. Another way that you can get your zeros, this is maybe an easier way for you, is you can just actually just literally plug in 0 for row. So come up here and just plug in 0 equals this. Zero it out. And as you solve this, based on all students take calculus, it will tell you what quadrant and where your zeros are based on that equation. Again, we've done equations. You should kind of remember that, how to do an equation. So if you zero it out, you can also get those. You don't have to do your chart. But in order to graph it, you have to do your chart. So I kind of like the chart method, but you do have to be careful. What if it's not on a 0, 30, 60? You might see it kind of like it. So once you get it graphed, if you see one, so if you see this thing coming out and you say, oh, I think maybe there's a 0 somewhere, well, then you need to make sure that you kind of plug in that number to see if it actually is a 0 for it. In this case, 0 is our only 0 for this one. So in other words, there's only one place that this does that. Now let me zoom this in a little bit. All right, so the reason this only does it in one place, you might say, well, but what about this right here? Isn't there one that's kind of like, no, there's not, because of the way it kind of curves out right there. So you can see it, the closer we zoom in, you can see where the pole, it kind of curves around this spot. So look at these two dots right here. You can't really put one here because it's going to cut through, like say at 30 degrees, it's actually going to cut through that thing as we zoom it in a little bit more. The only place that it zeroes out. Now there's some other places that it gets really close to 0, but the only place that it actually goes to 0 is at 0. So this one right here is the only branch tangent. All right, last thing that I want to talk about in this lesson is determining symmetry. What is symmetry? Symmetry is sameness, or being the same on both sides of either a point or a line or something like that. So in this polar graphing, symmetry looks just a little bit different. Notice down here, there's kind of some interesting things that it talks about. So it talks about it can be symmetrical to the 90, to the axis, there's different things that it can be symmetrical to. It can be symmetrical to the pole. So we're going to have to look at several different things. Also right here, there's a case that it might be symmetrical and it might not be symmetrical. So we'd have to do more testing to it. But it's not as simple as it is on the Cartesian plane. On the Cartesian plane, if it looks the same on the one side of the line that it does on the other, then it's symmetrical. It's a little bit different here in polar. So we have to have what's called symmetrical testing. So there's 3 different types of testing for this. Let's look over here at my screen. Polar equations symmetry test. Test number 1. We need to test it to the polar axis. This is actually fairly simple. Again, none of these things in this lesson are like, what's going on here? They're things that it should click to you when I say them. Like, you might not know exactly like why, but the math behind this isn't that challenging. So check this out. All we have to do is sub in a negative theta instead of a positive theta. That's it. Okay. Now we're going to work through it, but all we're doing to test polar axis. I would write these down. I would say test 1 to the polar axis, sub in negative theta. I would write down what you see on the screen right there. Because when you go to do these, you're going to need this, and this is not really written like this in the book. So I would write this down, and this is going to make your life a ton easier right here. To the polar axis, sub in negative theta. Test number 2, to the 90 degrees. So this is basically to the 90. Is it symmetrical to 90 degrees? Well, what we do is we sub in a negative rho and a negative theta. Test number 3, to the pole. What's the pole? That's the 0, 0. That's basically origin. And we would sub in negative rho for that one, okay? So there's 3 tests, 3 different sub-ins. One is sub in negative theta. One is to sub in both negative rho and negative theta. And one is to sub in just negative rho. Okay, let's look down here and let's think about this for a second. If the new equation is identical, so once we do all this, if the new equation is identical, looks exactly the same, then it is symmetrical. We're done. We check mark, yes, it's symmetrical. We move on with life. If not, then it might be symmetrical. In other words, it's not a yes or no. It's a yes or maybe. Once we get to maybe, okay, so in that case that we have a maybe, what you need to try is subbing in a matching point. What do I mean by that? Well, when we did our graphing, our polar graphing, remember that we have, like, for instance, sine is positive in the first and second. So those two points match each other, right? So it's the one is here and the other is here. It's just matching based on the first and second quadrant. Sometimes, like, tangent is in the first and third quadrant. So you're matching it in 2 different places. It's kind of like you have to find another that has the exact same value. Okay? So if 30 degrees has the exact same value as 120 degrees, we're looking for a matching point. And usually it's in the opposite quadrant, or the other positive quadrant, or the other negative quadrant. So if you have sine negative, then it's going to be in what? If it's 3, then it's going to be in 4. If you have cosine positive in 1, then it's going to be in 4, where the other matching point is, because you're looking for the other sign that matches. I hope that makes sense to you. If it doesn't, look through the book. They explain it just a little bit differently than I did. But hopefully the way that I explained it made it make sense. If not, look at what the book has to say, and maybe that will make sense for you. Okay, so here we are, and we want to just go ahead and work through this and sub through this. So our first one is we are going to check it for the polar axis. So that means we're going to sub in negative theta. So let's come up here and let's do that. Let's sub in negative theta. So here we go. We have rho equals 3 sine 2 times negative theta. Now, what would we do? We just keep solving this. We do what we can do. You might say, it doesn't look the same. Well, just wait. Let's work through it and see if we can get it to look the same. We would multiply these and get rho equals 3 sine negative 2 theta. Okay. Now, what do you know about this? We can take this sign and we can move it out front, right? So we have rho equals negative 3 sine 2 theta. So we got the sine 2 theta to look the same, okay? But out here we ended up with something different. Because of that, we would say that we don't know on this one. This is one of these maybes. So what do we do when we get a maybe? We come back here. It might be symmetrical, it might not. In that case, we need to sub in a matching point. Now, in order to do this, let's go ahead and jump back over here to the book. Let's look at something really quick. Let's look at this right here. So if the A point, this is, and we're using sine. So if this is our quadrant that we want, if this is going to have the same point, we would use this B point. We would sub in the B point on our angle axis, and we're going clockwise. So that would match up these two. A good way to remember it is just, okay, use this chart. Keep going back to figure 14E and say, okay, so how's this going to work? If I have sine and I want a positive sign, I'm going to use this B point. What's the B point? Negative rho, negative theta. If I have cosine, I'm going to use the D point. I'm going to use rho, negative theta. Okay. If I have tangent, I'm going to use the C point. Now, what if I have negative sine? Okay, so negative sine It depends on where it is, but if it's here in the third quadrant, then I would use the other negative sign quadrant, which is, so I would have to turn my rho positive, and I would have to turn my theta negative. I would basically take, if this is my point, I would take it and I would shift it to the next point. So you consider these points A, B, C, and D, and use this little chart right here to tell you what quadrant to put it in. I know that's a little bit confusing, but it's the best way to do it, trust me. All right, so we're going to come back over here and we're going to say, all right, so the polar axis was a question mark. We didn't know. So when we sub that in, we're using sines, so we're going to jump into the second quadrant using the chart. That means that my rho needs to be negative and my theta needs to be negative. Okay? So now I'm going to try to sub in using that. Negative rho equals 3 sine 2 negative theta. Okay, so I'll do the same thing that I did. Basically, before I ended up with this. And when I do that, I could multiply a negative through here and it would change those signs and I would end up with rho equals 3 sine 2 theta. Because it matches with the original, then I would say, okay, on my secondary test for test 1, then that ends up being, yes, it is symmetrical, because when I check the other side, the other sign point that matched my positive sign point, it was symmetrical. And in test number 2, it says we need to sub in negative rho and negative theta. So let's come back down here and look at it. Look at what we just did. I mean, we literally just subbed in negative rho and negative theta. So that one, we don't even have to do it again. When we did that, we know that it worked out. So sometimes these tests are going to kind of overlap each other. So in other words, we'd come here and we'd say, yes, that one works. So test 1 passed. Now, the first one was a question mark. We didn't know. But the second one, when we tested the other angle, the other positive sine angle, it worked. And then we come here, and this one ended up being the same, so we don't even have to mess with it. Next one, we're going to test it to the pole, and we're going to sub in negative rho. All right, so let's go back down here, and we're just subbing in negative rho. This one's a really simple one. You should be able to see it immediately. It's not the same. Yeah, we can't do anything else other than we could shift this over to the other side and say that rho equals negative 3 sine 2 theta. Those are not the same. We would come up here and we would say that that is not true. All right, let's look at this here where it says you can, for the B point, you can use this, or you can use rho, comma, 180 degrees minus theta. Basically, that puts you on going with the positive and then the 180 minus theta. So in this case, our theta was, let's say it's 30 degrees, whatever. So it would be 180 minus 30. So that would put you from 30 degrees, and that would put you over here at 150 degrees. So in this one, this last one, before we use the B point up here, let's use this rho and then 180 degrees minus theta to see how that works out. All right, so going back over here, rho equals 3 sine 2 times 180 minus theta. And so now what we would do is just kind of sub into this, and we would get rho 3 sine 360 minus theta. And then also, as we're doing that, let's look in, what's the test? The test is to sub in negative rho, so let's put negative rho in there. And so there we go. Let's look at what we get here. We get negative rho equals 3 sine 2 times 180 is 360 minus 2 theta. Okay. Now, one thing that we can say, when we get 360, that's the same as 0. So in this case, we can just kind of get rid of this, since 360 is just a wrap around the circle. So negative p equals 3 sine negative 2 theta. We'll move that out here. We get negative equals negative 3 sine 2 theta. And get rid of, multiply the negative 1 through that, cancel, cancel. rho equals 3 sine 2 theta, rho equals 3 sine 2 theta. So in this case, this would be, in this case, for this equation right here, rho equals 3 sine 2 theta, all three of the tests would check out, and we would get, yes, everything is symmetrical. You would do that same process if you had another equation and go through that to prove your symmetry. All right, like I thought at the beginning of the lesson, I thought, I'm not sure if I'm going to be able to get through all four of these. I didn't. So there's three of them. In the next lesson, I'll kind of pick up that last one, and then I will also teach the last lesson in this chapter. So hope you learned something there. Make sure if you missed anything to go ahead, slide it back, watch it again. And if you have any questions, just keep working through those and keep looking at those examples that I've given you and try to match them up. Look in the examples in the book and try to figure them out as you go. All right, that's all I've got for you. Hope you learned something there. We'll see you later. Have a good one.